Hello and welcome to Introduction to Intel Architecture training. Today we're going to be providing a basic introduction to Intel processors and specifically for the embedded market segments. Much of what we're providing today is of course generic as well, but again it's geared more towards embedded market segments. Really this training will be useful if it's been a while since you looked at Intel architecture or if you're familiar with other architectures. Really, again, providing the overview you would need to get started with Intel. Okay, so first I'm going to talk a little bit about what embedded means at Intel. Next, I'm going to turn it over to some content experts who are going to cover the basics of Intel architecture and are really going to focus on questions that often come up for folks who are new to Intel architecture. Next, we're going to talk about what it takes to boot a system, specifically what is a BIOS, what are the different ways to implement a BIOS, etc. And then we're going to go through a summary of the tools that are available, software tools that are available for Intel designs. And finally, we'll do a quick wrap-up and provide you some links to your next steps for getting started with Intel. Okay, so first let's take a look at what embedded means at Intel. Before we do that, I wanted to point out that at Intel we believe one of our fundamental strengths is in driving process technology in our commitment to Moore's Law. And Moore's Law really simply states that the size and the cost of transistors are reduced roughly by half about every 18 months. So what that means to you is ultimately higher performance, lower cost products, really with a focus on performance per watt that of course can be very important in embedded designs that have typically very limited thermal envelopes. So to do this, Intel spends a sizable amount of money on research and development and in developing these new process technologies. And we have a history of investing even through downturns, which is important as we continue through these sort of tough financial times. So many of you may know Intel for our desktop processors, our laptop, and our server processors. But Intel's Embedded and Communications Group has actually been selling into the embedded market segment for over 30 years. And embedded in Intel means a few different things. It might mean, for example, adopting specific products that meet embedded requirements. It may mean slightly modifying those products or pairing them up with different chipsets to provide, let's say, specific I/O for a particular embedded market segment. And sometimes it means creating new processors with the right thermals, the right reliability, and the right price points to fit many of these specific embedded and communications market requirements. And then most importantly, whether we adopt, modify, or develop these processors, we make them available for a minimum of 7 years, which of course is very important for embedded applications that with typically longer development cycles and longer expected life cycles versus, say, a PC. I just wanted to point out that embedded is actually one of Intel's 4 key growth pillars, as pointed out by our CEO, Paul Otellini. So it's important to note this because Intel has stated that it will continue to invest in growth areas such as the embedded market segment, which of course is important when you're choosing a vendor. You want to know that that vendor is as committed to the space as you are. If you haven't looked at Intel for some time, we do encourage you to take a closer look now. For example, you may be surprised that Intel now sells a processor at less than 3 watts, which can be critical for certain fanless applications or long life mobile type devices that are battery powered. Second, we have virtualization technology that can really help you take advantage of multi-core in the embedded space. potentially even if your code is not designed for a multi-thread or multi-core environment. And we've got some example use cases later on. Next, performance, and especially performance per watt. Obviously very critical for embedded applications, again with potentially restricted thermal envelopes. And finally, we have quite an extensive set of tools to help you develop, optimize, tune your applications, both for sort of single thread as well as multi-thread environments. And with that, I'm going to turn it over to Sam Fleming, who's going to get us started with an architectural overview.
So what I want to do real quick is give a high-level overview of the Intel architecture. Cover a little bit what the hardware looks like, talk a little bit about what some of the software architecture looks like. And one of the issues that's going to be coming up in this presentation and always in customer questions is what I call legacy. That's this little Kilroy picture here. And basically what legacy is, it's why Intel does some of the things it does. It's because that's the way the parts have been working for years, and Intel has to maintain that. And we'll bump into that in coming foils. So this is a block diagram of the overall Intel architecture. And again, this is a concept diagram. So these various blocks that we're going to be talking about move around inside the various chipsets. Start off with the CPU, and one of the things that's kind of important when you're reading Intel documentation is the CPU goes at the top, and that's not just a silly decision. Some of our documents are going to talk about southbound traffic, northbound traffic, and they're always kind of going back to this concept picture of the CPU on top. Some of our chipsets support multiple CPUs, and that's not multiple cores, which is multiple CPUs in one silicon package. This is actually separate pieces of silicon common in some of our high-end Xeon processors. They connect to a device that Intel calls the North Bridge, just kind of a generic term. Our documentation will also call this the GMCH or the MCH for Memory Controller Hub. And what a North Bridge is it's basically the interface between the processor, any DRAM interface that you have, and also if the chipset supports external graphics, that's usually hanging off the North Bridge also. The North Bridge is connected to another device that, the euphemism we use at Intel is called the South Bridge. What is the South Bridge? Simply put, the South Bridge is the garbage can. Anything that does not go in the North Bridge of the CPU winds up being on the South Bridge. So the South Bridge is traditionally where you have your older buses, your PCI up through PCI Express can also be off your South Bridge, but also all of your other functions that are in the North Bridge. Your SATA and PATA interfaces for your hard drive, your USB interfaces, mouse, keyboard, floppy, interrupt controller, real-time clock, interface to your BIOS. It's generally all in the South Bridge. Again, I just usually call it jokingly the garbage cans where everything else lives. And that's kind of a very high-level view of the various components of Intel architecture. Intel tends to break its product line into four pieces. Performance, which is essentially what I used to call our server platforms, and again, that's chipsets and CPUs that concentrate on usually high throughput I/O. Our scalable desktops, the standard desktop that sits in home users. We have our low power mobile chipsets, which is for laptops type of applications. And then the last product category is our ultra low power, which is our chipsets and CPUs geared for the lowest power use possible. This is kind of showing how the various components break up for the various segments. So here's our scalable and low power, very classically what was presented on the earlier page, CPU, North Bridge, South Bridge type of setup. DRAM interface on this is usually very high performance, dual channel, sometimes more of DDR2, DDR3. When you move into our server architectures, things tend to break up quite a bit. The example I'm showing here is Tylersburg, which is a chipset and CPU combo. In this case, multiple CPU Xeon processors. But in this case, with our latest processors, we've moved the DRAM controller up into the CPU. You'll also notice in this chipset that there's a lot of I/O throughput not going to the south bridge, but directly into the north bridge in this case. What I put here is lots of PCI Express ports, the number depending on what version of Tylersburg you end up using. And then of course you have the south bridge, the garbage can with everything else that's still present. And here in our last example, which is our ultra low power, this is our Atom processors. Again, a very small die, very small power. What Intel's done in this architecture is combined the functions of our North Bridge and South Bridge into one piece of silicon, which is our US15W chipset. Again, for lower power, you've only got one channel of memory on that, but everything that's not in the processor is in one component, the 15W chipset. Let's take a look at a very, very high-level view of the software architecture. Intel processors support basically two address ranges, one of memory and one of I/O. This foil talks about the memory address range. On older chipsets, it goes from 0 up to 4 gigabytes. That's your 32 address ranges. You'll see that 4 gigabyte come up in a lot of Intel documentation. And again, there's a lot of legacy issues there, which are kind of beyond the scope of this training. But our newer CPUs and chipsets, they have an address range that goes well above 4 gigabytes. I think they're up to about 64 gigabytes now in our last CPUs. The memory map that the Intel processors support, the DRAM is usually located there at the very bottom, so 0 to whatever your TOM, which is top of memory, is the DRAM. Everything above the DRAM addressing space is where the plug-and-play devices are mapped. Above that, the EEPROM, the BIOS, is generally right up at the top of 4 gigabytes. Again, one of those legacy issues. That's where it's been for the last many